Rahim. Ladies and gentlemen, in the previous video, that is in video number 472, I discussed the case of zero-sum game in which the various entries in the box sum to zero, so that was known as a zero-sum game. In this video, I'm going to discuss the prisoner's dilemma case and what it is. So let us discuss that. What do we mean by prisoner dilemma? So first of all, I would like to explain the background. The prisoner's dilemma was introduced by Tucker in 1940s, which is one of the most famous games that was studied in the game theory. The title stems from the following situation. There are two suspects which were arrested for a crime, and the district attorney had very little evidence in the case, and she was eager to extract a confession. She separates both the suspects and tells each of them, if you confess, that is, if you think on your companion, but your companion does not confess or does not think on you, I can promise you a reduced 1-year sentence, whereas your companion will get 4 years of sentence. If you both confess, you will each get a 3-year sentence. So this is what the district attorney tells each of the two suspects. Now each of the suspects also knows that if neither of them confesses, then the lack of evidence will result in being tried for a lesser crime for which they will receive only 2-year sentences for each. So this prisoner dilemma has two strategic players, that is suspects labeled A and B. There are two. One is labeled A and the other one is labeled B. There is also a district attorney, but because her actions have already been fully specified, there is no reason to complicate the game and include her in the specification. So we have just two strategic players, player A and player B. Each player has two possible strategies open to him, that is to confess or not to confess. So confessing means thinking, and not confessing means to remain silent in this case. Therefore, we write their strategies sets as SA and SB, and that is a set of two strategies, possible strategies, that is to confess and not confess. To avoid negative numbers, we specify payoffs as the years of freedom over the next 4 years. For example, if suspect A confesses but suspect B does not confess, then suspect A will enjoy 3 years of freedom and suspect B will have 4 years of jail. Therefore, the utility of A is equal to 3. So if A confess and B does not confess, then the utility of A is given by 3, and then this first entry is for the suspect A and the second entry is for the suspect B. So in that case, the utility of B is equal to 0 and the utility of A is equal to 3. Similarly, if the first player or player A does not confess and player B confess, then in that case the utility of A is equal to 0 and that of B is equal to 3. So that is what I just explained. If suspect B confesses but suspect A does not confess, then in that case suspect B will enjoy 3 years of freedom and suspect A none. That is, utility of B is equal to 3 and that is 3 years of freedom, and utility of A is equal to 0. He will face 4 years of sentence. So this is shown by this entry in this box. If suspect B and A, if A and B both confess, then we are in this cell, and then each of them will get 3 years of sentence. So they will enjoy 1 year. They will have they will have 1 year of reduced sentence, both of them, and they will both enjoy 1 year of freedom, and they will face 3 years of sentence each. Similarly, if both of them don't confess, then in that case each of them will get 2 years of sentence. That is, the utility of B is equal to the utility of B, and not confess, not confess. Suspect A does not confess and suspect B does not confess, and both of their utility is equal to 2. The confess strategy in this game is the dominant strategy for both A and B. Hence, these strategies constitute an example of a Nash equilibrium, and the district attorney's ploy looks successful. However, an agreement by both not to confess would reduce their prison terms from 3 to 2 years. That is, if both of them makes an agreement and they decide that neither of them will confess. So if neither of them will confess, then due to suspicion, their term of prison will reduce from 3 to 2 years. This rational solution is not stable. Although this is the best strategy, both of them gets minimum sentence, but this is not stable, and each prisoner has an incentive to squeal on his or her colleague. So this is then the dilemma, and this is what we know by prisoner dilemma, that the outcomes that appear to be optimal are not stable. So these outcomes seems to be optimal, but they are not stable. So this R is not O, or this is A R E. So sorry for the spelling mistake. Now we will discuss normal form of the game. What do we mean by normal form? The prisoner's dilemma and games like it can be summarized by the matrix that we just explained in the previous slide, and that is known as the normal form of the game. Each of the 4 boxes in that matrix represented a different combination of strategies and shows the players' payoffs for that combination. The usual convention is to have player A's strategies in the row headings and player B's in column headings, and to list the payoffs in order of player A and then player B in each box. That is, in each box the first entry is for player A and the second entry is for player 2 or player B. It needs to be mentioned that what we might predict will happen in the prisoner's dilemma. Looking at the figure or the matrix in the previous slide, on the first thought, we may predict that both will be silent. That is, both of them will confess. This gives the most total years of freedom for both, that is 4. That is 2 years of freedom for player A and 2 years of freedom for player B, and jointly they get the most total years of freedom for both compared with any other outcome. But if you think deeper, this may not be the best prediction in the game. Why? Let us suppose we may imagine ourselves in player A's position for a moment, and we do not know what player A will do yet because we haven't solved out the game. So let's investigate each possibility. Suppose the player B thinks on us, that is, he chooses to confess. By thinking ourselves, we would earn 3 years of freedom versus 0 years of freedom if we remain silent. So thinking is better for us. Now let us suppose that player B does not confess, but he remains silent, or he does not confess. Thinking or confessing is still better for us than remaining silent, because we get 3 years of freedom rather than 2 years of freedom. So consider this. So in both situations, thinking or confessing is a dominant strategy for us. Now, regardless of what the other player does, confessing or thinking is better for us than being silent because it results in an extra year of freedom. If we remain silent, we will get 2 years of sentence and 2 years of freedom. But if we think or confess, then we get 3 years of freedom. So because players are symmetric, that is player A and player B both are symmetric, the same reasoning also holds if we imagine ourselves in player B's position. Therefore, the best prediction in the prisoner's dilemma is that both will confess or both will think on each other. When we formally introduce the main solution concept, that is Nash equilibrium, we will indeed find that both thinking or both confessing is a Nash equilibrium. We will discuss that in more detail in the coming video. Now let us discuss the predictions of the game. The prediction has a paradoxical property. That is, it's a kind of paradox. By both thinking or confessing, the suspects only enjoy 3 years of freedom. But if they were both silent and confess and not confess, they would both do better because they will enjoy 2 years of freedom. Similarly, the paradox should not be taken to imply that pairs are stupid or that our prediction is wrong. It's not like this. Rather, it reveals a central insight from the game theory that pitting players against each other in strategic situations sometimes leads to outcomes that are inefficient for the players. So the suspects might try to avoid the extra prison time by coming to an agreement beforehand to remain silent and not to confess, perhaps reinforced by threats to retaliate afterwards if one or the other thinks. So introducing agreements and threats leads to a game that differs from the basic prisoner's dilemma, a game that should be analyzed in its own terms using the tools we will develop shortly in another video. So solving the prisoner's dilemma was easy because there were only two players and two strategies, and because the strategic solutions involved were fairly straightforward. It would be useful to have a systematic way of solving this as well as more complicated games. Nash equilibrium provides us with such a systematic solution. We will dedicate another video to discuss Nash equilibrium. Ladies and gentlemen, this was a brief discussion about the prisoner dilemmas case. I hope this was interesting for those of you who have a deep knowledge of the game theory. Kindly subscribe to the channel and don't forget to click on the bell icon so that you can get notifications about new videos that I'll upload for you. Thanks for watching this video. Kindly subscribe this channel and its various videos, and share its various videos with your colleagues, with your students, with your friends, so that they could also get advantage of this channel and various videos. Thank you, and see you in another video soon. Thank you.